Hello my dear students, welcome to my channel Dey Sir's Chemistry Coaching. Today I am going to discuss on the second part of coordination compounds. Okay, so please try to understand. This is d orbital splitting in an octahedral crystal field. You know that there are 5 types of d orbitals: dxy, dyz, dzx, dx square minus y square and dz square. They have same energy but different orientations in space. That's why d orbitals are called degenerate orbitals. So what are degenerate orbitals? The orbitals which have same energy but different orientations in space are called degenerate orbitals. For example, dxy, dyz, dzx, dx square minus y square and dz square. Say, consider these are the d orbitals of central metal in a coordination entity. When a ligand comes closer to the central metal, then the d orbital electrons get excited and reach into high energy level. As you know that any excited state is unstable, so the d orbital splits. The d orbital splits into different energy level. According to spectrochemical terms, the lower energy level is called T2G, which contains dxy, dyz and dzx, and the higher energy level is called EG, which contains dx square y square and dz square. So these are the 5 d orbital splitting in an octahedral field. O or not indicates octahedral. O stands for octahedral, remember it. This is called barycenter, where there is no splitting of energy. If you see it, the T2G energy level decreases by 2/5 del naught, while the 2 d orbitals, that is in EG, increases by 3/5 del naught. This is decrease, this is increase, energy decrease and energy increase. Okay, it is necessary to calculate crystal field splitting energy. Okay, today I will discuss. This is very important for your term 2. They ask to draw the diagram. The difference in energy between EG and T2G is called crystal field splitting energy. The difference in energy between the higher energy level, that is EG, and the lower energy level, that is T2G, is called crystal field splitting energy. Remember it. This is the diagram for octahedral crystal field. This is the diagram for octahedral crystal field. Different ligands have different capacity to split the EG and 2G energy level. Some ligands splits more, some ligands split less. So whenever we arrange different ligands according to their tendency to split crystal field energy, that is del naught, then we get a series that is called spectrochemical series. This is the most important for your time. What is the question? Define spectrochemical series. Write the series. Mention the strong field ligands and weak field ligands. So let's understand the spectrochemical series. This is spectrochemical series. As you know that it is an increasing order of the ligands according to their capacity of crystal field splitting energy. You know that different ligands have different capacity of crystal field splitting energy. So listen here. It's the increasing order of the ligands according to their tendency of crystal field splitting energy, that is del. This iodide less than bromide, less than thiocyanide, less than chloride, less than sulfide, less than fluoride, less than hydroxide, less than oxalate, this is oxalate ion, less than water. So up to water, these are called weak field ligands. Water is less than isothiocyanide, EDTA, you know that EDTA means ethylene diamine tetraacetate ion. Ammonia, this is EN, that is ethylene diamine, cyanide and cobalt. So these are all strong field ligands. So remember it, remember the strong field ligand, weak field ligand already comes, but this is the very important for, so you have to remember the series. During the hybridization of coordination compounds, the d orbital should vacate. If the ligand is strong field ligand, it can vacate or pairing up the d orbital, and in this case d2sp3 hybridization is there, d2sp3. If there is any weak field ligand, it has no capacity to pairing up the d orbital electrons or vacate the d orbital electrons. In that case, sp3 d2 hybridization takes place. So remember it, both sp3 d2 and d2 sp3 are same in their structure, that is, if two different complexes possess sp3 d2 or d2 sp3 hybridization, they have same structure, octahedral, but their spins differ. d2sp3 are called weak field complexes and sp3d2 strong field complexes or spin. You know that if you consider any coordination complex, that is a bracket part in solution, if you see under ultra microscope, it rotates on its own axis. There are some complexes which rotate slowly, they are called low spin complex or inner orbital complex. In that case, d2sp3 hybridization takes place. There are some complexes which rotates fast, a high speed, they are called high spin complex or outer orbital complex. In that case, sp3 d2 hybridization takes place. So let's understand the valence bond theory of hybridization in aspect of spectrochemical series. Valence bond theory of hybridization or VBT. According to valence bond theory of hybridization, coordination compounds mainly possess three different types of hybridization. Number one, sp3. If sp3 hybridization takes place, they have tetrahedral shape. Number two, dsp2. If dsp2 hybridization takes place, they have square planar shape. Number three, sp3d2 or d2sp3. In both of the cases, the coordination compounds possess octahedral shape. So let's understand the inner meaning of valence bond theory of hybridization. Remember it, during valence bond theory of hybridizations, the orbitals S, P or D which are taking part in hybridization should completely vacant. If the d orbital is not vacant completely, then ligands vacant the d orbitals. You know that according to spectrochemical series, there are two types of ligands. One are weak field ligands. From iodide to water, they are weak field ligands, and another strong field ligands from isothiocyanide to carbon monoxide, NCS negative to carbon monoxide. These are strong field ligand. Now listen, weak field ligands, that is from iodide to water, can't pairing up the d orbitals, because you know that during valence bond theory of hybridization, the d orbital of central metal ion should completely vacant, which d orbitals are required for hybridization. In that case, sp3d2 hybridization takes place, that is 4d orbital takes part in hybridization, not 3d, 4d. They are called outer orbital complex, outside the outer orbital. They are called high spin complex also, and in that case the main condition is that crystal field splitting energy for octahedral less than P for pairing energy. If there are strong field ligands, that is NCS negative to carbon monoxide in the spectrochemical series, then strong field ligands can vacant the d orbital. That's why in that case D2sp3 hybridization takes place, and as D in front of, so they are inner orbital complex or low spin complex, and in that case crystal field splitting energy of octahedral is greater than pairing energy. You understand now? So remember it, one of the very important question is there, mention different types of hybridization takes place in coordination compounds along with their examples. So listen, this is very important questions. I have seen a number of times in board exam. How many different types of hybridization takes place in complexes? Mention with example. So coordination compounds or complexes possess mainly three different types of hybridization. sp3, they have tetrahedral shape. The best known example is nickel tetracarbonyl. This is the best known example. Another is dsp2, square planar shape, and this is the best known example. NiCN whole 4 charge 2 negative. And the third one is either D2sp3 or sp3d2. Remember it, both have octahedral shape, but if D2sp3 hybridization takes place, they are low spin complex or inner orbital complex. If sp3d2 hybridization takes place, they are high spin complex or outer orbital complex. This is the difference. So this is board question. What is the difference between D2sp3 and sp3d2 hybridization? Listen, both have octahedral shape, but if D2sp3 hybridization takes place, they are low spin complex, while if sp3d2 hybridization takes place, they are high spin complex, and low spin complexes are called inner orbital complex and high spin complexes called outer orbital complex. You know that ammonia is a strong field ligand. So it can vacate the d orbital of cobalt, that is the central metal. That's why in this case D2sp3 hybridization. So in most of the cases, if there are strong field ligand D2sp3, remember it, the coordination number should be 6, that is octahedral. Here you know that fluorine is a weak field ligand, so it cannot capacity to vacant the d orbital of central metal cobalt. That's why the outer d orbital takes place, that is 4d, and that's why they are called high spin complex or outer orbital complex. So remember it, if the d orbital of the central metal is not vacant, weak field ligand cannot vacant it. If it is vacant, then no matter. If it is vacant, then this hybridization, but if it is not vacant, weak field ligand cannot vacant it, so the outer d orbital, that is 4d, takes part. So these are the hybridization, different hybridization in complexes. This is very important exam question, okay? Now try to understand how to determine crystal field splitting energy, that is del naught, on the basis of CFT of hybridization, crystal field theory of hybridization. Important question for your exam. Try to understand, very easy concept. Calculate crystal field splitting or stabilization energy for octahedral complex in case of D7 configuration, that is d orbital contains 7 electrons. One in presence of weak field ligand, or you can see in your exam where del naught less than P. Second, in presence of strong field ligand, or instead of this language, sometimes this is given del naught greater than P. How to calculate it? Understand, there may be 7 electrons, 8, 9, anything may be given. So here as 7 electrons are given, so put 7 electrons here, D7 configuration. According to Hund's rule, the electrons are filling up at first singly with parallel spin, then pairing takes place with opposite spin. 1, 2, 3, 4, 5, 6, 7. Here also 1, 2, 3, 4, 5, 6, 7. This is lower energy level, this is higher energy level, you know that, low, high. The filling up in case of weak field ligands, if there is weak field ligand, at first single takes place. So listen now, we have 7 electrons altogether, okay, we have 7 electrons altogether. So fill the electrons singly from lower energy level to higher energy level. 1, 2, 3, 4, 5. Still we have 2 electrons to fill. So again pairing takes place from lower energy level. So 5 and 2, 7 electrons. Here in case of strong field ligand, pairing takes place from the very beginning. So if there are strong field ligands, so from the very beginning pairing takes place. We have 7 electrons altogether, 6 electrons we have already filling up, so 1 goes up. So listen, if weak field ligand or del naught less than P pairing energy is mentioned, then fill the electrons singly. 1, 1, 1 go up. Then if available more, pairing takes place from the lower energy. For strong field ligand, just fill up the electrons from the very beginning. Pairing, then this. How to calculate del naught? There's the very easy concept. Total number of electrons into minus 0.4. Now here total number of electrons into plus 0.6 and add this. So listen, del naught, that is crystal field splitting energy for weak field complexes. Okay, there are 5 electrons here. So number of electron 5 into minus 0.4 plus total number of electrons 2 into plus 0.6. Calculate it and write the unit del naught. That's the answer. Positive or negative, no matter. If it is positive, write positive. If it is negative, write negative. So here, how to calculate it? Del naught equals to, that is crystal field splitting energy, equals to total number of electrons in T2g orbitals, that is 6 into minus 0.4 plus total number of electrons, that is 1 into plus 0.6. Calculate it and write the unit del naught. So remember it, we can determine crystal field splitting energy on the basis of CFT, that is crystal field theory of hybridization. In case of weak field ligand, fill the electrons singly 1, 1, 1, 1, 1, then if available more, pairing up. In case of strong field ligand, pair the electron from the very beginning and the rest in higher energy level. How to determine del naught? Listen now, what is the formula to find del naught? Del naught equals to, that is crystal field splitting energy, equals to total numbers of electron in T2g, that is lower energy level, into minus 0.4 multiplied plus total number of electrons, total number of electrons, total electrons into plus 0.6, and the unit is del naught. Listen once again. If we want to calculate it, how many number of electrons in T2g? 5 into this unit minus 0.4 plus total number of electrons in T2g, that is 6. Here total number of electrons, okay, I am calculating here, not this. I am calculating for this, okay. I am calculating for this, plus total number of electrons in EG, total number of electrons in EG, that is 2 into plus 0.6, and del naught is the unit. You may ask me, sir, how do you write it? Minus this minus. Listen, whenever I have drawn the diagram for d orbital splitting in octahedral field, I have told you that below it, below the barycenter, see the diagram, I have written 2 by 5 del naught, that is the energy of T2g decreases by 2 by 5, decreases by 2 by 5, decreases means minus, 2 by 5 means 0.4, and I have already mentioned you that in case upper than barycenter, the energy is increased by 3 by 5 del naught. 3 by 5 increases means plus, 3 by 5 means 0.6. That's why I have given here this and this, okay? You understand, I think. So the next topics, this is color. This year also you see one question relating to the color. Say one complex is given and they have mentioned why the compound has bluish color. Actually nothing is that. If d orbital contains unpaired electrons, then the electron by exciting moves to the higher energy level. As you know that higher energy orbital is very unstable, so the electron whenever jumps to the lower energy level, it releases some energy which we see in form of light, and the wavelength which matches, we see the light. There is one technique to remember the color. There are some complementary color pair. Say a light has red and greenish color, bluish greenish color. When the complex absorbs the bluish green color light, it becomes excited. But as you know that excited state is very unstable, so whenever the electron jumps to its ground state, it releases the energy, and at that time it shows a complementary color. So see about the color concept in complexes. So understand the concept of color of coordination compounds in terms of crystal field theory. Okay, now listen, this is the color entity. Okay, this is the color of light absorbed in certain wavelength. Whenever a complex absorbs color light, it has some wavelength. If d orbital is vacant, the d orbital electron shifts to higher energy level. As the higher energy level is very unstable, after some times it comes back to its ground state and releases energy which we see in the form of light. So this is the complementary color concept in coordination compounds. If any coordination complex absorbs color yellow, it becomes violet, blue green, red, blue yellow. And if these are all in visible region, okay, these are all in visible region, these are all in UV region, ultraviolet region. Listen now, if you consider this compound, titanium 6 water molecules charge is this. The question is that shows violet color. Explain. This is very important question. Okay, explain this shows violet color. Titanium has atomic number 22. The electronic configuration is argon 4s2 3d2. This is the valence shell. Here, if you determine the oxidation state of titanium, it becomes 3 because it has 0, so 3. So titanium releases 3 electrons from the valence shell, 2 from the 4s orbital and 1 from the 3d, because you have to remove 3 electrons. So the electronic configuration of titanium 3 positive is this, that is d orbital contains only 1 electron. So remember it, if d orbital contains 1 or 2 electrons, it can absorb light below UV region. Okay, it can absorb light below ultraviolet region. If there are 3 or more unpaired electrons in the central metal, it can absorb light in visible region. These are all visible region range. This is a UV range. Once again, if any central metal has 1 or 2 unpaired electron in d orbital, it absorbs lights in the UV region, and then it shows color according to the complementary color range. See, this complex has only 1 electron in the d orbital in titanium. That's why it absorbs light in UV region. And so it absorbs as violet color. The question is directly mentioned violet color. So see the violet color range. So you can write directly, it absorbs light, a blue-green light, it absorbs blue-green light in UV region, that's why it shows violet color. That's the only answer. This is very important question for your time. This is very important question for your time, okay? How do you explain the color? Clear? How do you explain the color? I think you understand it. Say, for example, another question, okay? See the another question. Say the question is cobalt NH3 whole 6 3 positive shows cobalt NH3 whole 6 3 positive shows yellow orange color, yellow orange. Explain. Okay, yellow orange color, explain it. Now listen, cobalt has atomic number, it's given 27. So here if you find the oxidation number of cobalt, it becomes +3. So if you write the electronic configuration, argon 18, 4s2, 3d, 18 plus 2, 20, and D has 7 electrons in the valence shell. As cobalt has oxidation state of +3, so remove 3 electrons. So cobalt trivalent ion has configuration argon 4s0, 3d6. So d orbital has 6 electrons. 1, 2, 3, 4, 5, 6. So you see that cobalt 3 positive ion contains 4 unpaired electron. That's why I have already told you, if the central metal contains 1 or 2 unpaired electrons, it absorbs light in UV region. If the central metal has 3 or more electrons, unpaired electrons, 3, 2 or 5, 3, 4 or 5, it absorbs lights in visible region. So cobalt, this absorbs lights in visible region. That is, it mentioned that yellow orange, so you can write that it absorbs blue color and thus it shows yellow color. It absorbs blue color because these are the visible region, yellow color. So I think you understand it, okay? I think you understand it. If you have any problem regarding this conception, you can write at my comment box, okay? So thank you for being with me. So please see all the videos, and I think these are very helpful not only for your forthcoming board exam but also for your entrance exam, okay? Thank you.